In this session, we study Gram-Schmidt orthogonalization procedure. So, M real valued signal which is of finite duration S1 of t, S2 of t, S3 of t up to Sm of t is represented by linear combination of n orthonormal basis function by this equation. So, this is nothing but M finite duration real valued signal which is energy signal is represented by sum of the product of these values where where we have to define some parameters here, constraints here, that is the time is finite here, I ranges from 1 to m and j ranges from 1 to n, and always n is less than equal to m. Here Sij, that is the vector value, is defined by this equation, that is I am multiplying the given signal finite duration energy signal with basis function and integrating over t duration for this constraint. In a similar way, n basis function which represented by orthonormal set, or when this is going to become orthonormal set, when integral 0 to t phi I of t phi j of t dt yields 1 for I is equal to j, and for I not equal to j it yields 0. So let us consider the signals which is of finite duration. S1 of t is represented by S11 phi 1 of t. S2 of t is represented by S21 phi 1 of t plus S22 phi 2 of t. Similarly, S3 of t, third finite duration energy signal, represented by S31 phi 1 of t, S32 phi 2 of t plus S33 phi 3 of t. What are these phi 1, phi 2, phi 3 of t? They are orthonormal basis function. That means signal Si of t can be represented by linear combination of n orthonormal basis function like this. Similarly, mth signal, that is I is equal to 1, 2, 3 up to m. It is varied from top to bottom here. Mth signal is represented by this equation Sm1 phi 1 of t plus Sm2 phi 2 of t up to the last term Smn phi n of t. Here I is varying from top to bottom, that is 1 to m, whereas j is varying from left to right, that is 1 to n here. Here I am going to represent S1 of t, that is first finite duration signal, in terms of the orthonormal basis function phi 1 of t and S11. Similarly, S2 of t, second signal, is represented in terms of second orthonormal basis function with the known value of first orthonormal basis function. And we have to calculate S21, S22 and G2 of t for the second signal. Similarly, S3 of t, that is third signal, can be represented by orthonormal basis function phi 3 of t by the previous steps orthonormal basis function, that is phi 1 of t and phi 2 of t, followed by the vector value S31, S32, S33, and then we are going to find G3 of t, some intermediate signal, and then phi 3 of t. In step 1, I am going to find S11 and phi1 of t, that means first vector value and orthonormal basis function, which is related to S1 of t. So let us consider the signal S1 of t as shown in equation 1. Here we consider S1 of t as basis signal, and we are going to neglect remaining portion of the values as 0. Therefore, S1 of t is represented by S11 and phi1 of t. So square and integrate the above equation over t seconds. Integral 0 to t s1 square t into dt, that is equal to s11 square integral 0 to t phi1 square t into dt. So whatever the term that is within this integration forms orthonormal set, because here two basis function are there, phi1 of t and phi1 of t. Because I is equal to j here, therefore it yields the value 1 or unit magnitude. So when you multiply this unit magnitude with s squared 1 1, we will get the value of S11 here. Therefore, we can take the square root of this equation, which yields the value of the first vector value of the first signal S1 of t, that is given by S11 is equal to square root of integral 0 to t S1 square t into dt. Once S11 is available, S1 of t is known, so it is very easy to calculate phi1 of t. Therefore, phi1 of t is given by S1 of t by S11. In a similar way, we have to express S2 of t, that is second finite duration energy signal, in terms of second orthonormal basis function phi2 of t. So S2 of t is the linear combination of orthonormal basis function as shown, S21 phi1 of t, S22 phi2 of t. So phi1 of t is nothing but the first orthonormal basis function we obtained from the previous step. Here in this equation, that is equation 2, S2 of t is known, S21 is not known, S22 is not known, phi2 of t is also not known. We only know phi1 of t from previous step. Therefore, here phi1 of t, with the knowledge of phi1 of t, we are going to define phi2 of t. So square that is to find S21, multiply and integrate equation 2 over t seconds by phi1 of t, because phi1 of t we know. So on multiplying and integrating, we are going to get on left hand side integral 0 to t s2 of t phi1 of t dt, that is equal to s21 is a constant. Here when you multiply phi1 of t by phi1 of t, you will get phi1 square of t into dt, plus here s22 into integral phi1 of t phi2 of t dt. When we observe right hand side here, the first term in right hand side forms orthonormal basis function, because I value is equal to j. Therefore, the term within this integration yields 1 or unit magnitude. The second term on right hand side is having different value. I is not equal to j, therefore it yields 0. Therefore, we write S21 as integral 0 to t S2 of t phi1 of t into dt. So here the second subscript represent the second finite duration signal, and first subscript, that is one subscript, represent the first orthonormal basis function. So now, with the knowledge of S21, we know S21, phi 1 of t we know from the previous step. S2 of t is known. Two unknown terms we have to determine. Therefore, from equation 2, I am going to consider a intermediate signal G2 of t is equal to S22 into phi 2 of t. So, here we have to calculate G2 of t first in order to find phi 2 of t. S2 of t we know, S21 we already calculated, phi 1 of t we calculated from the previous step. Therefore, obtain G2 of t using this equation or known terms. So once G2 of t is known, then we can able to find phi 2 of t. Phi 2 of t is G2 of t by S22. Still S22 we don't know. Let G2 of t be S22 and phi 2 of t. So on close observation of equation 2 here, known terms are S2 of t, S21 and phi 1 of t. So these two terms are not known. Therefore, let us consider it as G2 of t. So now we can find what is G2 of t with known values. So G2 of t is represented by S2 of t minus S21 and phi 1 of t. So G2 of t is known now, but S22 and phi 2 of t is not known. So in order to obtain one of the values, that is S22, that is second vector value or real number, you square and integrate equation 3 over t. So that is S22 square integral 0 to t phi 2 square t dt is equal to integral 0 to t g2 square t into dt. So the term within this integration represent orthonormal basis function set, which is yielding 1 for I is equal to j. Therefore, we can get S22 value as in square root of 0 to t g2 square t into dt. Once S22 is known, G2 of t is calculated from the known values. Phi 2 of t, that is second orthonormal basis function, is represented by G2 of t by S22. The next step is to determine third orthonormal basis function to represent S3 of t. So in order to represent S3 of t in terms of phi 3 of t, consider the equation S3 of t can be represented by linear combination of orthonormal basis function. Here, phi 1 of t is calculated from first step, phi 2 of t obtained from second step, and S3 of t is known. S31, S32, S33, phi 3 of t not known. That is the vector values, and third basis function is not known. So in order to find S31, S32, use the shortcut method, that is S31 is given by S3 of t into phi 1 of t. That is nothing but you have to integrate the third signal with the first orthonormal basis function. Similarly, S32 is given by S3 of t phi 2 of t. 3 subscript represent the third signal and 2 subscript in S3 to represent second orthonormal basis function. So we are now able to define S31 and S32. So here we have to write dt, here we have to write dt. So in a similar way, we are going to define the intermediate signal G3 of t as S3353 of t, because S31 is available from this equation, S32 is available from this equation, phi1 of t, phi2 of t obtained from previous equations, that is steps. Therefore, this term is not known. So let us consider this term as G3 of t and obtain G3 of t in terms of known terms by using this equation, S3 of t minus S31 phi1 of t minus S32 phi2 of t. Once G3 of t is known, obtain S33 by squaring this equation and integrating over t. So when you integrate both sides over t by squaring, we get S33 is equal to square root of integral 0 to t g3 square t into dt. So once S33 is known, G3 of t is known from the values, we can calculate the third orthonormal basis function as G3 of t by S33. Like this, the procedure continues. In a similar way, we can write the expression for the fourth signal, for example, S4 of t. So we are going to write the equation for fourth signal. So S4 of t is represented by combination of orthonormal basis function and vector values like this: S41 phi1 of t plus S42 phi2 of t plus S43 phi3 of t plus S44 phi4 of t. So what is the value of I here? I value is 4 and j is varying from 1, 2, 3 up to 4. So here phi1 of t is known or calculated from step 1, phi2 of t is calculated from step 2, phi3 of t is calculated from step 3. So which are not known here? So these values are not known here. That is, S41 is not known, S42 not known, S43 not known, then S54 of t and S44 is not known. Therefore, we can obtain the expression for S41 like this. 4 stands for the fourth signal S4 of t, 1 stands for the first orthonormal basis function. Similarly, S42 is nothing but the fourth signal multiplied by second orthonormal basis function and integrate over t duration. Similarly, 43 S43, the third real value, is given by integrating S4 of t with the third orthonormal basis function. So once S41, S42, S43 is known, phi1 of t, phi2 of t and phi3 of t is already known. So let us consider this S44 and phi4 of t as G4 of t. So what is G4 of t? G4 of t is nothing but So let G4 of t is S44 into phi 4 of t. So we don't know what is S44 and phi 4 of t, but we can calculate what is G4 of t from the value S4 of t is known, S41 phi 1 of t is known, minus S42 phi 2 of t is known, minus S43 phi 3 of t is known. Once G4 value is available, now you square and integrate this equation over t duration. So that is integral 0 to t g square 4t into dt, that is equal to S44 square integral 0 to t 5 square 4 t into dt. So whatever the term that is there within this integration follows orthonormal set. Therefore, this yields 1. So the value yields 1. Therefore, I can write S44 square, that is given by integral 0 to t g square 4 t into dt, that is g4 square t into dt. Therefore, on taking the square root, S44, that is the real vector value, is given by square root of integral 0 to t g4 square t into dt. So once S44 is known, that is here it is known, so we can calculate phi 4 of t. So what is phi 4 of t? Phi 4 of t is nothing but the orthonormal basis function to represent fourth signal, that is given by here G4 of t divided by S44. Like this, the procedure continues. This is the method of representing M finite energy duration signal using orthonormal basis functions. So this procedure is called Gram-Schmidt orthogonalization procedure. We will solve some problems on this in order to understand the concept.